I'm just gonna have to. I gotta go through the trenches and just do this shit. I know this is nothing, but so I got my stat coming in. I know this is nothing, but yep. So I got my stat coming in. Okay. Okay. What I want to find this next struct. Okay. Basically. Oh, I defined it right here. Or didn't define it. I initialized it. Let's do ST mode actually, because I need to here's what I need to do. This first one I need to actually I need to create a new struct. Oh, I was starting to create the struct here. I mean, yeah, I just represent this as a string, right? 1, 2, 3, 9, right? Or 10. So do do 11. I forgot that hold on. Let me look up that 1 means. Let's see. It's this number. Permissions, number of hard links. Okay. need these to be pointers. Actually, no. 50 on those, that should be enough for. See if it's on here. Mm-mm. Apparently I'm supposed to do this. This is the man page. Where is it? Here it is. There we go. Okay. Need AI help with this one, but oh, I already have type text, so I don't need to put that. Okay. We're gonna do this for oh, I need okay. Okay. Calm down. Wait, I need to put this in a function. Oh, hey guys, gonna help me with this, but then username, owner of the file. Oh, here's hard links. I already have that. Dude, I'm so confused. How do I need to use entry stat? Or entry.dname. Right? I need something. Yeah, this is what's confusing me, and I don't need this. I need to have these, like, yeah, they have to be over here, right? They have to. See if it really lets me do this. Oh, I can't. They should be pointers. I just want to point them to. I just want to point them to here. There, now it's pointing to this. Oh, that's an end. Really? Okay, we'll just do end for now. And we're gonna print this shit. pop time. Okay, that's easy. Alright, I'm done with this for a while. I'm going back to. I just can't. I don't know. Back to this.
Hey guys, welcome back. We're talking about structures today, right? So what is a structure? Why does this matter in C? And how do we use them in C effectively? So we talked a lot about things like pointers and arrays. And the thing about arrays in C is that an array is what? A contiguous block of memory that allows you to contain up to n numbers of the same type, right? The problem with that is if I want to logically combine multiple variables of different types to create some kind of object or structure, I don't really have that opportunity with arrays, right? I can't make a character pointer and an integer and a float associated just normally without structures. So what is a structure? A structure is the association of memory values to one location so that they're logically organized. So for example, if I have a struct cat, right, what I can do is have a few things. I can say character name, right? So this allocates a char pointer for every cat that I make. I can have an int age. Probably want to make that an unsigned int because you cannot have a negative age. Unsigned. Signed. There we go. Typing is hard. And then I maybe want to have a, I don't know, an int biscuits, right? Also unsigned. And so what we're doing here, guys, is we're just making a logical grouping of different variables and the way we want to use them in the future, right? Because if I had name 0, age 0, and biscuit 0 for up to n number of cats, it gets very hard to manage, but doing it this way is very easy. Okay, so how do I logically group these? So how do I use these? To use the cat structure, I have to say just the type of a variable like anything else, struct cat, and then I can do the name of the cat. We'll call him Frank, right? Now, by default, what actually happens here is memory gets allocated, but not in a way that is good, right? We're not initializing the variable Frank. This is not super safe. We don't want to have uninitialized pointers, for example, that could be used later. So one way we can allocate memory for Frank is just do this. We'll set all of the contents of Frank equal to 0, which is good. We also can initialize Frank by variables. We can do .name is equal to Frank, right? That's his name. We can do .age equals 32, old cat, and then biscuits, unfortunately for Frank, biscuits is 0, right? Frank has no biscuits, he's very sad. Okay, so we now have a cat whose name is Frank, and we can access these variables now, right? We can say printf %s is %d years old with %d biscuits, and we can access them via the dot
Oh.
operator Frank. Which means it's a local allocation, meaning Frank is out of scope anywhere else, right? We can't use Frank unless we pass around a pointer to Frank. We can now access Frank via the pointer to Frank. Now what we'll notice is that the use of a struct pointer creates some different functionality or different of syntax for how we deal with structures. So if I made, for example, let's do this. Make a function called void give cat biscuit. This is derailing very hard. What is a biscuit? And this will take a struct cat pointer, right? And now to access the struct cat pointer, we actually have to do one of two things. First of all, we want to say if cat is equal to null, right? If the pointer were given given is null. Just get out of there. Don't want to deal with that. But next, what we want to do is do cat. We want to access the biscuits and make it plus equal to 1, right? Well, because the type of struct cat is not a struct cat, it's a struct cat pointer, what we actually have to do is this arrow notation. A struct pointer creates some different function at the Frank. Name is equal to, for Frank, Biscuits is 0, right? Frank has no biscuits, he's very sad. Okay, so now have a cat whose name is Frank, and we can access these variables now, right? We can say printf %s is %d years old with %d biscuits. Hey guys, welcome back. We're talking differ. You cannot have a negative age unsigned. Unside of cat. Contents of Frank 0, right? Frank has no biscuits. He's very sad. Okay. The biscuits. And we can access them via the dot operator, frank.name, frank.age, and frank. Biscuits. Very simple. This function, like if you don't know what the stack is, Frank-ality or different of syntax for how we deal with structures. So if I made, for example, let's do this. Make a function called biscuit two things. First of all, we want to say if cat is equal to null, right? If the pointer we're given is null, just get out of there. Don't want to deal with that. But next, what we want to do is do cat. We want to access the biscuits and make it plus equal to 1, right? Well, because the type of struct cat is not a struct cat, it's a struct cat pointer, what we actually have to do is this arrow notation, right? This arrow notation is literally the same as the dot notation to get a field for that structure. It's just when it's a pointer, we use the arrow notation, right? So we do cat biscuits plus equals 1, and then return, right? Very simple. So let's do this. Let's take this line. We're going to yank this. We're going to make another copy of it over here. And then we're going to say give cat biscuit of the address of what's his name? It's Frank, right? Because again, the input parameter to this function is a struct cat pointer. Frank himself is a cat, struct cat, we need to give the address of Frank to do that, right? So give cat biscuit. And just like from the previous function example, it may be a good idea to have an enum that describes the ways this can fail. Type def enum result good, result bad, right? Again, literally just riffing here, but these are a result.
Come on.
To how we're going to deal with it. 0 years old with 0 biscuits. Frank is 33 years old. We're going to deal with this in the key value store project, the new project coming up in the course. But we also, now that we've defined the struct cat, we can use that definition or pointers to that definition in other definitions, right? So if we do struct family, we'll call this a cat family, right? We now can do struct cat double pointer members, and we can do struct, or let's do a char star name, right? What I'm doing here is I'm allocating space for a pointer to a list of pointers of members of our family, right? So if we want to use this cat in the family of cats, we can do it this way, where we now can associate these to other cats via some structure, right? What I'm getting at here is when we get into the key value store stuff, guys, this will be kind of like our key value table, and this will be our key value entry, right? The way we'll do this is we will create room for all these entries inside our table entry, and then have associated functions that will initialize, update, remove, and delete those entries in our table, right? So guys, these are structures. Again, what's cool about C is, like, at the end of the day, all you have are primitive types, int, character, float, those like bool, and then you, and pointers obviously, and then you structure them in a way using structures that logically describe a type, like a bigger, like more complex type, and then you make functions that take user input and output associated with those types and make it print and receive and write data. That is all of C, right? If you understand this, you understand a lot of the C language. Obviously, there's like algorithms and stuff that get a little more complicated, but generally, guys, if you get this, you understand the code. So we'll move into the next lesson, and we'll see you there. Take care.
Hey guys, what is up? Welcome back to your next lesson in Zero to Hero C programming on Low Level Academy. Today we're talking about unions. Now, unions are not super relevant to the course project that you're going to be writing at the end of the course in Module 12, but I think it is important to talk about because it's one of those things that people probably see in code as they're maybe reading other code bases and don't really know what a union does. So in a struct, for example, or a previous project or a previous lesson, a struct will allocate enough memory to contain all of these elements, right? I want to have enough room for an ID, and then 64 bytes for a first name buffer, and then 64 bytes for a character buffer, float income, etc., right? So it's going to allocate all the memory for all of these types. Now, the union type is a little weird. It's a little different. So a union will create enough room for the biggest element. You're probably kind of curious, like, what purpose does that serve? So let's do my union U. Just call it a union. It'll create enough room for the biggest element. So for example, if I have int x and I have char c, the union will only be int x wide, which is 4 bytes on the system that I'm using right now. The reason for the union type and why it kind of exists is if, for example, you were doing embedded stuff and you wanted to have access to all 4 bytes within the 4-byte int type and didn't want to have to do the manual math every time, what you could do is by looking at the value c, you would get access to the first byte of the 4-byte character x. I know it's not like super relevant for this project here, but just understand that a union is a type that only creates enough room for the biggest element, and you're allowed to access all the sub-elements. And I can do like short s, for example, right? But let's kind of show you guys how this works. So I'll make a union, my union u, we'll just call it u. We'll say that u.x equal 41, 42, 43, 4. And what I'll do is I'll print all the different parts of it. So I can do %hx, which gives you half. And I'll give you %hhx, which gives you half of half, so a quarter. And then I'll print that and I'll give it we'll show you the short u.s, and we'll do u.c. And this will show you basically that when I'm using the union, I set the larger value, and by using u.s and u.c, I'm accessing internally the smaller parts of this bigger X. I know, super weird, super complicated. Don't worry about it for this project too much, but it's just good to be aware that this exists. Do gcc taco union, union.c, we'll run union. Yeah, so again, by showing you, we made the value hex 41424344. By using union.s and union.c, we got access to the internal short and the internal character of that larger int x. So keep going, don't worry about this too much, just under all the memory for enough room for the biggest element. You're probably kind of curious, like what purpose does that serve? So let's do my union u. The union will only be int x wide, which is 4 bytes on the system that I'm using right now. The reason for the union type and why it kind of exists is if, for example, you were doing embedded stuff and you wanted to have access to all 4 bytes within the 4-byte int type and didn't want to have to do the manual math every time, what you could do is by looking at the value c, you would get access to the first byte of the 4-byte character x. I know it's not like super relevant for this project, u. When I'm using the union, I set the larger value, and by using u.s and u.c, I'm accessing internally the smaller parts of this bigger X. I know, super weird, super complicated. Don't worry about it for this project too much, but it's just good to be aware that this exists. Do gcc taco union, union.c, we'll run union. Yeah, so again, by using larger, more complicated memory management related in our project, you're super tight so that we know exactly where the memory is. We'll see you there.
I don't know what the hell this is. Like what?
In the 4-byte int that u by using u.s and u.c, I'm accessing internally the smaller parts of this bigger x. I know, super weird, super complicated.
Wait, what if I just do this? Forgot. So that's 0. Is it ever gonna be 1? This is gonna break it, but yeah. What? I have mouse. Yeah. Yeah. We're done. Yeah, I don't care. Actually. Whatever for now. What? Okay. I'm not.
Hey guys, what is up? Welcome back to your next lesson in Zero to Hero C programming. Today we're talking about dynamic memory allocation, what that means, how you can use it incorrectly, and how to use it correctly. So in our previous lesson, we talked a little bit about how we use structures and pointers together to create code that performs logical functions with data that may be out of scope, right? So for example, we created this employees array here, and I passed the address of the first employee to this function to initialize it, and previously we printed that data out. Now there's an issue with this code from a performance and optimization standpoint, where every time we run this code, despite the amount of employee space that we need, we are always allocating 1,000 employee structures on the stack. Now we don't want to do that for two reasons. One, it limits us to the amount of employees that we can allocate. We can only ever allocate 1,000. But also B, we're kind of wasting memory here, where every time we run this program, we're blowing up the stack, and it's kind of just a waste of memory, right? So what we can do instead is we can use a memory allocator, and glibc, the libc that you use by default in GCC, has a memory allocator, and you use it in the following way. So instead of employees being an array here, We're going to now treat employees.
Okay, but where? How do I call this? It's just employees. Let me type this out because I don't know how does this work. Where's my ampersand?
As a pointer, right? And when you do a pointer type, it may point, kind of just a waste of memory, right? So what we can do instead is we can use a memory allocator and glibc, the libc
I just gotta lie. Whatever.
See that you use by default in GCC has a memory allocator, and you use it in the following way. So instead of employees being an array here, we're going to now treat employees as a pointer, right? And when you do a pointer type, it may point to one element, but you actually can use this pointer to point to an infinite number of elements further out from the base element, right? So now instead of employees being an array, employees is now a pointer.
That can be.
And we're going to set it
right?
equal to malloc, right? So malloc is the memory allocator. We're asking libc to return to us a pointer to some amount of memory. And how much memory do we want? We want the size of struct employee t, right? That is 140 bytes, as we saw before. So we're going to ask how big a structure employee t is, times the number of employees that we want. So we could use our max employee structure here, or the max employee's value, and get 1,000 back. But what's cool about using malloc is now instead of using some gigantic constant, we can actually use a runtime value, like I say int n equals 4, for example. We can use int n equals 4, we can use n to only allocate the amount of employees that we need. Now it's good practice to make sure that you check that your pointer did not get null returned, because sometimes the memory allocator can fail, and if it returns null, well then we don't want to use that memory because we can't dereference null pointer, right? So we can say like printf the allocator failed, allocator failed, and then we return -1, which is the bad error code, right? This is us telling us that the code failed. And then otherwise we do the exact same thing. We initialize the employee, we use the ampersand to get the address of the employee, and we go from there. And then now once our code is over, we need to give the memory back to the allocator, right? So when you're using code that uses dynamic memory allocation, it's really, really important to avoid what is called a memory leak, where effectively the memory in your code does not get given back to the operating system, and over time you can actually allocate all the virtual memory allowed for your process, and the kernel will end up killing your process, and it's bad voodoo, right? So what we want to do is once we're done using this memory, we write free employees, and this will give the employees value back to the allocator. And what we want to also do is make sure that we set to avoid employees. We can actually use struct employee times the number of employees that we want. So we could use back. But what's cool about using malloc is now instead of using some gigantic constant, we can actually use a runtime value, like I say int n equals 4, for example.
Okay, that's it.
Your pointer, null pointer in there. And then now once our code, you can actually allocate all the virtual memory allowed for your process, and the kernel will end up killing your process, and then we write free employees, and this will give the employees value back to the allocator. And what we want to also do is make sure that we set employees equal to null, right? Because if we have this for free, so by self is of 0.income, that we'll do a little GCC. We're gonna get a bunch of warnings here because I didn't include standard lib. Let's actually go ahead and include standard lib. So as you're using new functions, by the way, in C, what you want to do is do man that function, like man malloc, and make sure you're including the header file that comes with that function, right? The C compiler knows what you're talking about and will do it for you most of the time, but it's good practice to do it yourself, so your code behaves correctly. Good, so we have that, and now we have 0 dynamically allocated, not statically allocated. That's dynamic memory allocation at a high level. Effectively, what we're able to do is, instead of depending on compile time values or values that we know in our code, we can read data off the disk. Like maybe the database header says that, you know, we have n number of employees, we have 4 employees, so this value came from the database header, right? And now, instead of allocating 1,000, right, we can allocate a runtime value, n, and then use that later on in our code. So that's it for now. Next lesson, we're talking about static memory allocation, which is another kind of memory allocation that happens in the program in the data section. But we'll talk about that in the next video. We'll see you there. Hey guys, what is up? Welcome back to your next lesson in Zero to Hero C programming. Today we're talking about static memory allocation, and in particular I'm talking about the use of the static keyword and kind of what it does, how it works, and where it makes sense to use it. So let's say, for example, we wanted to track in our employee database the amount of employees that had been initialized so far. We could do this kind of in 2 ways. The first way is by making a global variable, right? We could say int n employees equals 0. And we'll say this has actually a G in front of it to show that it's a global variable. So we'll say G num employees. We'll do some like camel case stuff here. Now, global variables are kind of a no-no in programming for a few reasons. The main reason being it's hard to track exactly where this piece of data is accessed and control who has control over it at any given time. And especially later on in our code, when we do multi-threaded code, it gets really difficult to make sure that this is accessed in a way that's sane, there's no data races, etc. So what we can do instead of using a global variable is do what is called a static variable. So let's say in our initialize employee function here, I want to use the static keyword. What the static keyword will actually do is it initializes this variable in global scope, but we are the only ones that have access to it. What that means is that every time the function gets called, this variable does not change its value, right? So to use static variables, what we'll do num employees, we'll do static int num employees equals 0. The first time this code gets ran, it'll be set to 0, and that'll be in a global scope, meaning it'll only get set to that value 1 time. And then when we run future lines of code after that initialization line, we can do num employees plus plus. That means incremented by 1. This will increment the number of employees variable to 1 plus the previous value, even though it gets set to 0 here. What actually is happening is this variable lives in what's called the data section of the ELF. So it's not being put on the stack, it's being put in a location that does not get destroyed when the function returns, and then updating that variable for us. What this does is it actually gives us a practice called data hiding, where we could have made this a global variable, but by putting it in here, other functions can't access the num employees variable. We can't, like, no one else can touch this but us. So it's just a really good way of hiding data so that there's no race conditions. What we actually could do is we could now make initialize employee return an int, and it's gonna return int num employees, right? We also could make the ID equal num employees. So now every time we initialize an employee in the database, the ID gets set to the current index. So maybe it's 0 the first time, then it's 1 the next time. And then after that, we return the ID that we got. So let's go ahead and turn this into a loop and say for int I equals 0, I less than n, I plus plus. Right? And then what we'll do is we'll initialize employees of I. Then we're going to printf new employee ID is %d. and then we're going to print. We'll do an int in here, call it int ID. We'll print their ID, right? Go from there. We'll delete all this, and we have to make sure we still free the employee thing because that came from the malloc, came from the heap. And then we set n equal to 4. So let's go ahead and see if we get 4 employees, each with a different unique ID. New employee, ID is 1, ID is 2, ID is 3, ID is 4. So static variables are a really cool way of having global-ish data, but keeping it so that the scope of the variable is local to that function, so only you can update it, and then you can use that to return data or add it to logic of your function or whatever. So that's it for right now. Let's go on to the next lesson where we talk about the heap is kind of a scary place. How do we check to see if we're using the heap properly? And if we aren't, how do we check for memory leaks? We'll see you guys there.
Hey guys, what is up? Welcome back to your next lesson in Zero to Hero C programming. In this lesson, we're talking about these things called pointers to pointers or double pointers. Typically, this is a concept that trips a lot of people up when they're learning to code in C because it's a weird concept. Pointers on their own are kind of difficult. You then introduce this additional layer of complexity where you have a second layer of pointers, and people tend to not understand why they exist or how they work. So I want to go into that in this lesson because this will actually matter a lot for the end of course project. So let's dive into it right now. So we've talked about pointers very recently, right? A pointer is just a variable that contains an address of another variable, right? And in this example here, we have the integer I. Int I is just a space on the stack that contains the value I, and I is just some number, right? Now, what we can do is we can take the pointer to I by creating an integer pointer. So we say that int star pi is equal to the address of I. When we create a variable declaration, the left side of an equal sign, this type with the int star means it is a pointer, right? We've talked about this before, pretty straightforward. The additional layer of complexity comes into place where we have this to star thing, right? So again, talking about pointers left to right, the int star star named ppi is equal to the address of pi. So all we've done here is we've created a variable that is a pointer to a pointer whose name is ppi, and its value is equal to the address of pi. And that makes sense, right? Because it is a pointer, it is the address of a type which is a pointer. Now the question that really bothers people, and again, like this from a conceptual standpoint is very simple, right? But how, like, why does this matter? Why do we do this? Well, take for example the case where we are getting a pointer back from some kind of dynamic memory, right? Like we have malloc. Malloc's going to give us a pointer to data that lives in the heap. We're going to use that in the employee database to store our employees. But the thing is, if we have this pointer come back from malloc, how do we give it back to the program? If this pointer to the data lives in one function, but I want to use it in a different function, how do we do that? Or even more particularly, if we reallocate the pointer, if we change the value of data, how do we update it? The double pointer is going to give us the power to put the data pointer somewhere else. We're able to use a pointer to update the pointer with a new address. So for example here, we have this function called foo, and inside of foo, we call malloc. Malloc returns a pointer, and we want to extract that pointer outside of the foo function so that we can use it. Now you might be thinking, okay, isn't that the whole point of a return value? And that is one way we could pull the pointer out, but we also in functions want to return some kind of status, right? So instead of returning the pointer from the function, we're going to return this type we made up called a status t. It just says if we did or did not fail in the function. That's not super important, but what is important is there is a parameter here that is a pointer. It is the data out. And the reason that it's a pointer is it is the address of an address. And what we're able to do is instead of calling malloc, getting the variable out, and then returning it by the return value, which we can't do because this is a status t here, we're able to overwrite the value at data out by saying star data out equals that value. We're using this double pointer as a way to extract data from the function and set the value at data out to this new malloc location. And this will be used in the employee database when you have to expand or contract the size of your employees based on if you add or delete one. You will need to reallocate a heap buffer, and you're going to have to extract that pointer via a double pointer. I'm gonna go write a snippet of example code real quick. So to kind of show how our double pointers work, I made this cute little example, right? So here on line 24, we have a pointer to an integer that comes from the heap via malloc, and malloc allocates 64 bytes, and then we call our function foo on the address of this pointer. That turns this label here into a pointer. And what foo will do is foo will try to reallocate the pointer to a particular size. And we can go through and read foo here. So foo returns a status t, which is a type that I made up that just says good or bad. And we're doing this so that we can tell the programmer via the return of foo if something inside the function went wrong or went right. It's just another way of designing your functions. So the foo signature takes an int pointer, which is an address of an address, and then the length. We have a temporary pointer, and we try to reallocate this data pointer, and reallocate just makes a malloc buffer bigger or smaller. we say realloc the thing pointed to by data, because that points to our pointer, to a certain size. If temp fails, we are going to set that pointer equal to null, because now it failed to reallocate, and then we're going to return status bad. Otherwise, if it passes, if all of the stuff goes well, what we're going to do is we're going to say the thing pointed to by data is equal to this new temp variable. So we're literally overwriting this address with this new address, because realloc is returning a new pointer from the heap. And if this fails, we say uh-oh, otherwise we just go on and use rest of our program here. So in this example, all we're doing is we are taking a address to a pointer, which is now a pointer pointer.
I think it should be the other way around. Like, do the foo function first, and then I don't like that. I don't know how this is a pointer though. A pointer pointer. That just looks like a pointer to me.
And we're using that to overwrite it with a new pointer from a function like malloc, for example. And that's it. So if we run this, we should see that the program A doesn't crash, but also B doesn't say uh-oh. So let's do that. We'll do gcc taco double.c, and we'll run double, and we're good to go. So that's it, guys, the temp variable. So we're literally overwriting this address with this new address, because realloc is returning a new pointer from the heap. And if this fails, we say uh-oh, otherwise we just go on and use rest of our program. And we try to realloc this data pointer, and realloc just makes a malloc.
I guess it's still returns an address of data.
Buffer bigger or smaller. We say realloc the thing pointed to by data, because that points to our pointer, to a certain size. If temp fails, we are going to set that pointer equal to null, because now it failed to reallocate, and then we're going to return status bad. Otherwise, if it passes, if all of the stuff
Oh man. Alright, what are we doing here? Okay. Size T. Let's size T out. Shut up, Daisy, please. Okay. So this points to a pointer. I just gotta remember this returns a memory address where this can live.
Goes well. What we're gonna do.
Okay, I get it now. First, yes, that is a pointer to a pointer because this returns. What's this return? Memory address, and this is initialized as a pointer. Figured it out. Yeah, I'm retarded. Starting to make sense. Alright, so what's wrong with this? That double pointer, that's not how double pointers work. Well, I'm dereferencing. I think I need this. Yeah. Yeah, Steve references it once. Thing is, I don't know what the input is, which makes it a little confusing. You know. Then we dereference twice. We dereference first memory address, and then we get our initial memory address, dereference, and that leads us to the next memory address, and then we dereference that memory address, and that points to the actual value that we want to overwrite. So now that memory address points, now that chain reaction points to a new value. It's rewritten.
Hey guys, what is up? Welcome back to your next lesson in Zero to Hero C programming. Today we're talking about how to detect and fix memory leaks in your code. So like I said previously in the past couple lessons, it's better to use the heap in some instances where you want to have dynamic memory allocation, where the amount of memory you want to access is a function of some variable that you have at runtime, right? The issue with malloc is that it's an allocator. You're borrowing memory from the system. You need to give that memory back to the system, otherwise you have what's called a memory leak, where effectively over time the amount of memory your program uses grows over and over and over again. Eventually you may consume the entire system's memory, your program can crash, etc. It's just bad practice. You always want to give the memory back. So in this code, I'm not going to say exactly where, but we have a memory leak. We have a place where we do not give the memory back to the system, and I want to figure out where that happens so I can fix it, right? Now there's two ways we could do that. We could do a manual source code audit and look for it ourselves. The problem is that when we do this, there's a lot of runtime issues where, you know, maybe to trigger the memory leak, we have to run 2 commands in a row and then run a third command. We're not going to figure that out when we're looking at the code statically. Instead, we can use this tool called Valgrind. Valgrind is a really powerful tool that people use all the time to check if there is memory loss in their programs. What Valgrind actually does under the hood is it actually wraps the heap and keeps track of allocations and frees, and will tell you like, oh, you lost track of this chunk of code here, or this chunk of memory here, you know, you're never gonna get that back. Go look at this line of code to fix it. So to use Valgrind, what we have to do is first compile our code with this tacg flag. The tacg flag, what it does is it gives us debug symbols in our code and gives Valgrind access to specific lines of code where things happen, so it can tell us where to go and fix our code. So compile it with tacg. You will see that your program has probably exploded to some huge value now. That's good. You want that debug information in your code for Valgrind to play with. And then to install Valgrind, sudo apt install Valgrind. I already did that, so I'm not going to do it, but you had to do that for us. And then what we're going to do is we're going to do Valgrind tactech leak check equals full pointers and then tac s. What this will actually do is it'll run our program. You see it running here, and then it's going to tell us exactly, you know, what happened on the heap and what went wrong. So our leak summary is that we definitely lost 48 bytes in one block of memory. So there is a 48 byte chunk of memory that we did not allocate properly. Oh, 48 bytes. Yeah, obviously. Okay, I was thinking of the previous. I was trying to figure out it was only 48 and not 140 times 4. Anyway, 48 bytes in one block of memory, and it actually will show us exactly on what line that allocation happened. So pointers.c line 30. Let's go there. Struct. Okay, so now we can see that the malloc for our employee buffer never got freed. Oh, right. I deleted that line to show you guys the example. So we can do free employees like this, and we'll do gcc taco, Valgrind, and we will see all heap blocks were freed, no leaks are possible. So that is a very high level way of using Valgrind to check your code to make sure that it has no memory leaks. Obviously in production code like this, we'll have to make sure that our code has full coverage, meaning that, you know, in this piece of code, here, there's only one code path for this code to take, right? It'll run this way every time. If we had more complicated code where there are some more conditional statements, you know, it may leak sometimes, it may leak other times. We need to add that logic into it that gives us, you know, full code coverage, that all of our lines of code are running in the order that Valgrind expects it. So anyway, that's it for right now. Thanks for watching, guys. Like I said in previous lessons, please take this data, take this information, use it, understand it, absorb it, write some code yourself, get your hands dirty, write some code that leaks, try it out in Valgrind, you know, figure out how this stuff all works, and use that to move on to the next lesson. When you're comfortable, we'll see you there.